some limiting concentration, or not limiting concentration, but some concentration where the chemical potential is at its lowest point. As you move up in concentration from there, the chemical potential increases, indicating that it's becoming less energetically favorable to stick another ion in solution. And so we talked about all of these attractive forces that cause the chemical potential of an ion to be lower in solution. But that said, past certain concentration limits, the chemical potential starts to rise up again because of unfavorable interactions. And in that case, this limiting law, log gamma plus minus is A, negative A, whatever, doesn't work. And so it has to be replaced with an equation that corrects for those observed effects on concentration. And we're going to see that equation next, I believe. I said this once, I just repeat it real quick. So we said that A value right here on the argument of that exponent or whatever is specific to your solvent. For water at 25 degrees Celsius, it's about 0.509, and that's what A is. So you'll see that limiting law oftentimes for aqueous systems expressed with an 0.509 in front of it. Repeating myself real quick here. This was the graph I drew you. I showed chemical potential decreasing as concentration of the ions increased. This graph communicates basically the same material. It just recasts it in the form of natural log of gamma plus minus versus the concentration of the system, or the concentration of ions in the system. So if this axis is increasing concentration, this axis is the natural log to get gamma plus minus. And our limiting law predicts that gamma plus minus decreases kind of linearly with concentrations. As more ions you put in, the lower that chemical potential becomes. This bold line is basically what that limiting law suggests. The observed behavior is something different. The observed behavior is that at the limit of dilute solution, you do have that linear relationship, but that as the concentration increases, boom, that log of gamma plus minus increases, indicating that the chemical potential is increasing, right? So we can correct for this observed behavior by looking at the Debye-Huckel extended law. And the Debye-Huckel extended law, again, we're not going to derive it, but it's got a couple of terms in it that you should pay attention to. And these are concentration-dependent terms. These are terms that are a factor of the ionic strength. So when we said that I, the ionic strength, is the sum of the charges raised to the power to their coefficient times the concentrations. Obviously, the more ions you stick in solution, the larger that ionic strength becomes. And you see that the ionic strength multiplies a term in the numerator of the negative term, and it multiplies ionic strength to the 1/2, multiplies that term B, and ionic strength to the first power multiplies this constant C, which is the positive part of this equation. So overall, this equation tells you what logarithm you're going to need to get the ionic strength. This term has a negative coefficient in front of it, and so it tends to, as it grows larger, the ionic strength decreases, right? Or sorry, gamma plus minus decreases. This term, as it grows larger, the gamma increases. Ionic strength down here makes the negative contribution smaller. So the larger the ionic strength is down here, the larger this term in the numerator is, and the smaller that negative coefficient, or the negative coefficient is going to be. The larger the ionic strength is, the larger this term will be. And so this drives the log towards positive values. Essentially, this equation accounts for what we see up here in the graph. At low concentrations, you're kind of reduced to the limiting law because I is approximately 0, so B times I is 0, and we end up with a term that is this divided by 1, and we get back the limiting law. This term over here, as I goes to 0, as the ionic strength goes to 0, this term goes to 0. And so again, in the limit of dilute solution, we get back the limiting law. But as the concentration increases, this whole term gets smaller, this term gets larger, and we now have a gamma plus minus that's growing in size, therefore we have a chemical potential that's growing in size. So this limiting law essentially just corrects for those kind of unfavorable interactions that take over as we increase the concentration of ions past some max or some concentration where interactions are most favorable. Does that make any sense at all?
Yeah, we use this equation in quant.
What's that?
We use this equation in quant.
It's
Yeah,
kind of,
did you take
okay.
quant with?
All right. So as long as you guys are good with it.
We had to solve for it. Yeah, we had to do the we had to do the extended versus the normal one and solve the two different outcomes.
What is sine was? What is
We learned the extended one. We learned the extended one and the normal one, and solved for both of them. We did at least. No, but you did. No, wow. He's doing it again this semester.
Okay, so going to kind of get to a different theme here. We're going to move back into the same stuff, but we'll talk about a different piece of logic for a second. When you apply a potential across a solution, something happens. Sometimes the solution conducts electricity. It still does things even if it doesn't conduct. I'll try to explain to you what I know it does. Potential is applied to a system by essentially taking a capacitor and sticking it at opposite sides of the system. A capacitor is a piece of metal that's had a potential put across it, and so there's a buildup of negative charge on one plate, and there's a buildup of positive charge on the other plate, and this creates a field across that system. And if you want to know how these fields are calculated, go take electromagnetism. They always go back to this equation. So you can use that equation, that R squared force law equation, to derive what the magnitude of the field is between those two plates as a function of the magnitude of charge built up on the plates. But essentially, we're just building an electric potential across that system by putting charge separation across it. The system, or the solution that feels that, is going to move its positively charged ions towards the negative plate of the capacitor, because it's attracted to the electrons, and it's going to allow its negatively charged ions to move towards the positive plate of the capacitor. If the field is small enough that the plates can't donate their negative charges to the positive ions, or they can't pull the negative charges of the negative ions away and donate them to the positive plate, if the field's not strong enough, then you'll just have kind of a net migration of negative charge one way and positive charge the other way. And the system will set up a field that points in the opposite direction. The solution will have a field that points in the opposite direction to the applied field. So essentially, systems that have electric potentials applied across them act to try to minimize that potential by establishing a potential in the reverse direction, establishing fields in the reverse direction. If the fields are sure, if the potential is strong enough, then the charges will end up being ripped off of the negatively charged ions at the positive plate, and charges will be donated to the positive ions at the negative plate, and you'll have a current that flows through the system. And so this is what happens when a system is conducting electricity. You've got electrons being ripped off of these negative ions over here, or negative ions that move over here, the electrons will be ripped off of them until they go to that side, and the positive ions that are over here will pick up electrons. You watch this happen with water, and you end up seeing hydrogen gas and oxygen gas bubbling up at different sides of the system. A lot of the things that you use in the lab use an alternating current, so the thing moves back and forth, and you don't see as much gas evolving from those guys. In the event that you do have a current that's flowing, the size of the current is just going to be how much charge is passed per unit time. The size of the current is going to be a function of several variables. Variable number one, and this is the one we're going to consider in more depth, is mass transfer. And when we talk about mass transfer, we just showed that the negative ions have to move to the positive plate, the positive ions have to move to the negative plate. To get there, they need to move through the solution. So negative ions from the bulk need to move from the bulk into the positive plate. Positive ions from the bulk need to move over to the negative plate. And to do this, they have to migrate through the solvent. The solvent has other ions in it. It's got solvent molecules, there's viscosity, there's forces that the solvent is pulling onto the ion with. There's forces that the other ions are pulling on to it with. And so all of these things end up affecting how fast an ion can move through a solute as it approaches the different plates of the capacitor. Once the ion gets to the capacitor, once it gets to the plates, now you have to start wondering, or you have to start factoring in the effect on the rate due to the particular ion that you're using. Some ions pull on electrons more strongly than others. Some ions want to give up their electrons more strongly than others. And depending on just how much force is required to pull that ion off of, or to pull the electron off of the ion, or to pop the electron onto the ion, some reactions will move faster than others. And so electron transfer, once you get to the plates, also affects the rate of electron movement. So the magnitude of your currents, size of your conductivity. For some systems, there are chemical reactions that need to happen to either follow or precede electron transfer. In a system that has some kind of a chemical reaction that's requisite, then you'll have to also consider the effects of those reactions, the rates of those reactions on the transfer of current. But essentially, we've got mass transfer, how fast is the ion moving solution, we've got electron transfer, once the thing gets to the plate, how quickly does that electron pop off, and we have rates of any other reactions relative to the process. Can't really get into the rate of electron transfers unless we start looking at the actual chemical potentials of the production potentials, oxidation potentials of the species. But we can talk about mass transfer in terms of kind of general properties of the ions. So when an ion's moving through solution, it's got two things that are kind of pulling on it. holding it back. It has whatever interactions there are from other ions around it. We said that when you got ions in solution, a negative ion in general is going to be kind of surrounded by positive ions, and as it tries to migrate through that solution, if it passes a positive ion is going to pull it back, kind of retard its movement. We said that in general, being an ion in solution lowers your chemical potential. This means that you're bound with stronger forces essentially to that solution. And so you can imagine that the higher the concentration of ions, the slower, or the higher the concentration of counterions, the slower a given ion will be able to move through the solution, because it's held back, its movement is retarded by those forces that are pulling on it. And so we expect that conductivity is going to decrease as the concentration of ions increases, because those forces holding you, keeping you from moving, are larger. These are ion-ion interactions. You've also got forces between the ion and the solvent. So we showed that water can hydrate ions, and so it can hydrate ions, it can exert dipole-dipole forces, or dipole-monopole forces on ions. Any given solvent is going to retard movement at some level. And so the rate of speed with which an ion moves through the solution is going to be a function also of its attractive forces with the solvent that it exists in. We have an equation, a general equation for the conductivity. Again, conductivity is just a question of how quickly ions can move through that solution. Oh, it's also a question of how quickly the electrons can get popped off. We've got this term, molar conductivity. It has a limiting value, and it has a correction to that limiting value. The correction goes as a constant conductivity times the concentration of ions in the solution to the 1/2 power. This term is the term that corrects our conductivity for those ion-ion forces that we were talking about. The larger, the more ions that there are adjacent to you when you're trying to pass the solution, the slower you move. And so your conductivity decreases as concentration increases. So this term essentially adjusts for those effects. You've got your limiting term. Your limiting term is going to be the conductivity in the event that the solution is so dilute that as you move through it, you don't ever really pass another ion. And so you're not pulled back by that ion. In that case, all that is holding you back in your movement is the forces with the solvent. And so you'll have some limiting conductivity that's a function of how tightly the solvent holds you in solution and prevents you from moving from one side of the solution to another. And that's what this A naught is. That A naught can be expressed for a given solution as the contribution to conductivity from each individual ion. So you imagine if you've got a solution of sodium chloride, and sodium's moving towards the positive pole, and chloride's moving towards the negative pole, that they'll have different relative mobilities in that solution, right? Chloride might be held more strongly by the solvent than sodium, in which case chloride would move faster and sodium would move slower. So chloride would contribute more to the conductivity and the sodium would contribute less. I don't know if that's the actual effects. I have to go look at a chart to see which one of those two ions is actually mobile. But that said, we can break apart each individual ion's conductivity in the limiting case into terms that account for its attraction to the solvent and the pull that it feels from the field. Let me show you how to do that. So, you guys know what terminal velocity is?
Yep.
Right? You got a particle that's accelerating under the force of gravity, and it starts to move faster and faster and faster, but as it speeds up, the force of drag slows it down because the force of drag increases. The faster you're moving, the more drag you have, the more friction you have. Well, ions in a solution like this behave the same way. When they feel that chemical potential, it's like a gravitational force that's starting inside it, and they start being pulled in whatever direction the potential is pulling them. And they start moving faster and faster and faster, but as they move faster, those drag forces become larger and larger, and at some speed, what happens is the two forces are equalized. The force from the pull of the field is equal to the drag forces, and so some of the forces ends up being zero, and so acceleration stops, but you still have some velocity, so you're still moving now at constant velocity through that solution. This happens for an ion. We call it a drift speed, and it affects its mobility. I showed this equation too early. I wrote it down in the notes too early, but mobility is E times concentration over 6 pi Na. We'll show you right now where that comes from. Real quick before we move forward, just note that in this equation, Z is the charge on the ion, A is the radius, and this, I don't know the names of my Greek letters, whatever that one is, the N, that guy is a function of the viscosity. So this guy accounts for the magnitude of attraction between the ion and the solvent. You see that mobility decreases as the radius increases. Basically, the larger the size of the ion, the more surface area over which it interacts with the solvent, and so the more it's retarded in its movement. The viscosity N of the solvent affects the movement, right? It's a measure of how tightly the solvent tends to attract something in general. And then we have charge in the numerator, which says that mobility goes up with charge. Mobility increases with charge because the more charged you are, the stronger the forces are that you feel from the potential. So keep track of those variables. Radius, mobility decreases with increased radius, decreases with increased frictional forces from the solvent, and increases with the charge. So we set these forces equal to each other. The force that pulls the ion towards the plate is a function of the charge of the ion, right? We just said that, the larger the charge, the larger the force. E is the electronic charge, so it's a charge on one electron. Number of coulombs in one electron, or the little e, and the big E is the magnitude of the field. The larger the size of the field, the faster that thing moves. So the force is propelling the ion through the solution. E times the absolute magnitude of Z times the big E, power of the field, strength of the field. These are going to be equal to the retarding force. The retarding force is a function of the ionic radius A and viscosity of the solution. Set these two forces equal to each other, and we get this variable S. I would have called it V, but the people that wrote your book called it S for speed, so we're just going to keep their notation. We get that value S. That accounts for the increase in the retarding force as you speed up. So those magnitudes of those forces increase with size. Set these guys equal to each other, and we have an equation that says that the speed of an ion is proportional to this thing times the size of the field. We give this thing a name. We call it U, the mobility. And so the speed that an ion goes through solution with is a function of the mobility of that ion times the magnitude of the field. Right? Pretty straightforward stuff. If you look at data on the different ions, and you look at their actual ionic radius and their mobilities, you'll see that a lot of ions with smaller ionic radiuses have large mobilities, and that ions with larger ionic radiuses have smaller mobilities. But we just said that the speed goes as 1 over A, the radius, which is telling us that larger size ions should actually migrate slower. The data says the inverse. And that ends up becoming a function of these hydrating water molecules that each ion carries with it in solution. Smaller sized ions, because the magnitude of the force becomes stronger with the smaller size r, smaller sized ions are able to hydrate more water molecules for some reason than larger sized ions. Big ion, you're actually going to end up having fewer water surrounding it in solution. And so the radius of the unit that actually travels, when an ion travels in solution, it carries its hydrated water molecules with it, and the radius of the ion that's traveling in solution becomes larger for the smaller ion because it attracts more water molecules. So the smaller size ions end up actually being larger size when we're talking about how they move through the solution. So the conductivity of individual species, we said that the speed that it travels to the solutions with is the mobility times the magnitude of the field. You've got charge traveling with some speed. To know how much charge crosses a boundary per unit time, you'll multiply just the charge times the speed. So your conductivity, the amount of charge that moves through a given space at a given time, is going to go as the size of that charge times the speed with which it travels. I think that kind of wraps up, it felt anticlimactic, that kind of wraps up what we need to talk about in terms of mobility. We're going to have, you're going to have a homework problem, and you'll see that, that the conductivity of weak acids can be used to determine the Ka values, the dissociation constants. And so essentially, if you know what the conductivities of individual ions are, and you know how much a solution would conduct if a given amount of those ions were in solution, if you then go to the case of a weak acid, where you say that you've got incomplete dissociation, so HA goes to A minus plus H3O plus, K is equal to conc A minus conc H3O or conc HA. By knowing how much a solution would conduct if all of the ions were dissociated, if you had complete dissociation, you have all A minus and H3OA or H3O plus in solution, you can look at the actual observed conductivity and you can figure out just how much of those ions are in solution. And so you can use that to determine the extent of dissociation for that species. So all this stuff that we're doing has real practical applications. Okay, so